Hey guys, I'm voicing over this video. This one's going to be on LC circuits, or particularly we're starting off with inductors, but I'm speeding it up 120%. And as I voice over, we're going to try and talk through the different things I'm writing, just so it doesn't take so much time for you guys to watch the handwriting here. So let's review a little bit about inductors and inductance. And again, I apologize, the camera keeps zooming in and out because it's try and zoom in on my pen, which sticks up, and then it tries to zoom in on paper, and so on and so forth. In any case, okay, so let's say you have this coil of wires. The current goes in from the left, goes out the right. Um, the current goes. Um, if you're facing the right, it goes clockwise. If you're facing the left, it goes counterclockwise. So if I lift the paper up, that'd be like if you're facing to the left, um, it goes in a counterclockwise loop. So you can kind of see my hand gesturing the direction of the current. Um, and so then the magnetic field points in the direction of the thumb. In other words, if you lay your hand with the never mind. Okay, so just just watch um, the way I'm drawing the magnetic fields, right? So from there, you can use your right hand rule to figure out which direction the coils are actually turning. So alone with just the current, it creates a magnetic field, but that's not what inductors do. Inductors start to really do their thing when you have changes in current. As your current changes, that results, let's say, for example, a positive change in current. So you're increasing the current that results in a change in magnetic field. So as the magnetic field increases, you have an increasing flux to the right. So then it will try and create a current or a EMF that opposes that change in magnetic uh, flux, and so you'll have a current that actually goes from right to left. Instead of left to right, it goes right to left. So it'll try and create a magnetic flux to oppose the increasing flux to the right. And in order for that to happen, you'll have an induced current, basically the opposite direction. And we kind of talked about this. Basically, every time you have induced current, it opposes increasing current or increasing field, at least for coil of wires, right? You have current going to the right. If it's increasing, your induced current will be to the left. It'll oppose. Um, and so that essentially kind of creates this EMF, um, a potential difference where it's higher potential on the right, lower potential on the left. And again, the actual potential may not be this, um, but the difference, right? It'll create a difference compared to what it was before. Okay, so let's kind of look at this mathematically here. As I doodle with something. Yeah, okay, here we go. I think. Yeah, yeah. All right. So writing out the EMF. Um, the EMF essentially being that potential difference across your inductor. Your inductor, the symbol we generally use for inductors are L. And so by Faraday's law, right, you have the change in flux, but change in magnetic flux through your coil of wires versus time will be your EMF. And so since the area is not changing, it's only the field that's changing. You can break your flux up into the magnetic field part and then the area part, and there are n loops. So, however many loops there are, that that's how many times your field is crossing that many loops, right? So it's n times a. Now the field, we've done this before. The field from a solenoid is given by the equation there, and so then your flux is you throw all your mu naught in over L in there, um, and then you're gonna differentiate that, right, with respect to time. And all those numbers or all those terms are essentially constant except for the current. The current's the only thing that's changing with time. So yeah, simplifying some things. Okay, I pull the I out specifically so that when I take the derivative. Uh, all the constants stay in the front. I'm sure I was saying some things in my mind while I was writing this. I can't remember what the details are, but essentially you can simplify it out. And all the constants there, we call that inductance. We assign it the value inductance. Those are all geometric values. The little L on the bottom, by the way, is the length of your inductor. So from left to right, how long that is. The A is the cross-sectional area, or essentially the area of a loop, and it's however many number of loops. And then when you put in the combination shown, uh, that's the value for inductance. Right, so at the bottom there, you can see the potential induced, um, or the potential across your inductor as your current changes is just L times the rate of change of current. Um, Another way you can look at L is just comparing it to the magnetic flux. Um, but again, at the end of the day, L is real. Your inductance is a geometric value. Um, so that's how you get um, the induced voltage across the inductor. Okay, so now let's take a look at what happens if you um, put it into a circuit. Okay, let's compare uh, inductors and resistors because they're circuit elements. Um, what's important here is deciding where, in what direction, does it increase potential or decrease potential. Okay, so if you compare it to a resistor, uh, if you follow the current, resistors are a potential drop, right? So that's why your change in V, as you go from left to right across your resistor as the current goes to the right, is a negative I times R. It's the same thing with uh, inductors. Um, your your uh, potential across that inductor is a drop from left to right as long as you're following the